Hello and welcome to my channel. Uh, Starstruck Rambler here. Um, today we are continuing with our space series, and today we'll be talking about the planets that were formed during the early stages. Now, after the first stars and galaxies formed, and after the universe was seeded with the more heavier elements, um, elements that were heavier than hydrogen and helium, like carbon, oxygen, potassium, calcium, for example. Um, that's also when the first planets started to form. Um, all this, all these stars and galaxies, black holes, and planets formed within about 1 billion years after the Big Bang. And now the oldest planet that we've found so far, called Methuselah, has an age of about 13 billion years, which means that it formed about 700 million years after the Big Bang. So, the first planet started forming less than 1 billion years after the Big Bang. Um, my throat is a bit dry today, but anyway, um, so far we've sorry about this. Throat is really dry, but yeah. Um, so far we found something like 6 to 7 thousand or more potential planets. About half of which have been confirmed. Now, these range in size from about Mercury size, which is about the smallest that we found so far, to several planets which are way bigger than Jupiter. Now, I don't have the names with me right now, or their mass, or the exact masses, but I will give that in the next video. But this is just a rough video of what we found so far. But the smallest planet um, is about the size of Mercury, while the largest has several times the size and mass of Jupiter. Um, Now the largest ones are obviously gas planets, while the smaller ones are more like Neptune, for example, Uranus, or super Earths. Um, let's see, what was that one planet's name? Okay, I'm not sure on the name right now, but I will let you guys know in my next video about this. With more names and sizes and masses. Um, but the largest rocky planet that we found so far is yeah, basically a its nickname. It's been nicknamed the Godzilla of the rocky planets. And it has a mass of about 17 Earths, which is abnormally large for a rocky planet. Now, normally, planets of this size are gas giants, or more closely to ice planets like Uranus and Neptune. But now, for some reason, this rocky planet is yeah, rocky. But like I said before, normally planets this size are termed gas or ice giants. Now this is because of their high gravity, um, they are more able to hold on to a dense hydrogen atmosphere. Um, Now Earth can also hold on to a dense atmosphere, but if you have a planet that has a mass of 10 or more Earths, then it becomes a gas or ice giant. Now I say ice giant because of Uranus and Neptune. Now an ice giant is made of rocky and metallic material, as well as material that's normally frozen, such as water and ammonia, for example, and a hydrogen helium atmosphere, such as Neptune and Uranus. Now, ice giants, they orbit so far from their host stars that these materials, such as water and ammonia, are frozen normally, um, which is why they are called ice giants. Um, but because of the heat they produce, they are partially liquid as well, or at least, well, we're not sure on the exact nature of the interiors, but the material or the stuff that they're made of is normally frozen at that distance that they orbit the stars. Um, but with this massive planet, um, it was actually a bit of a surprise to find such a large rocky planet with such a um, thin atmosphere for a planet of that size and mass. Because normally, like I said, planets of this size are normally gas or ice giants normally. Um, Now we're not sure on how exactly it formed because of we have a model or several ideas of how planets form, and this planet just doesn't fit into what we um, have an idea of. You see, when stars form, they have a lot of material, gas, dust, and other material, but mostly gas and gas, dust and gas, and it is from this stuff that planets form. Um, Now, within a certain distance, um, around most stars, there's this line called the frost line. Inside the frost line, rocky planets form, and outside of this frost line, gas giants form. This is because inside the frost line, the temperature of the star is high enough that only solid stuff like silicates and metallic elements can survive, but things like water, for example, they can't survive in that area of the system. But outside of the forest line, water forms solids, solid ice, and it is from this material that gas and sorry about this, guys. Um, yeah, beyond the frost line, with these icy materials, it's from this that gas and ice giants form. Yep, and from what from what we have observed so far, this massive planet just doesn't fit into into this model. We're just not sure how it may have formed because according to the model that we have or models, it just shouldn't exist as it does right now. But yeah, it's there, it exists. So now we have to find a way to explain how it may have formed. Now, I will do some research as well and see if I can find anything about that as well. Um, also, I, also I will look up more names of planets and their sizes and masses. Um, Now, one of the systems I can name now, or two, for example, the several Gliese systems, or for example, the more recent Trappist Trappist 1 system. Now, I can actually talk about that quickly, the Trappist 1 system. Now, as some of you may have heard, um, this year we've discovered several planets around the Trappist 1 system. Now the star was already known um, over the last few years to have several planets around it, but now this year they've discovered more planets around this star, and all of them are roughly Earth-sized and mass, which means that they have a size and mass quite similar to that of the Earth. Um, Around about Mars to just slightly bigger than Earth, with a slightly with a slight lower density. Now we have found 7 roughly Earth-sized and mass planets around them, with 3 of them being in the habitable zone. Now, the habitable zone is where it's this zone around the star where liquid water can exist. Too close and water boils away. Too far and water freezes. Now our solar system is a more or less good-ish example. Venus is in the red zone where water or where the temperature is too hot for water, while Mars is in the cold blue zone where where the temperature is too cold for water. Basically, it freezes there, while Earth is um, is in the green zone where the temperature is right for water. Yeah, as you may have noticed, I used the red, green, and blue zone for our star. Now, with the sun, this there's this zone around it where where there are different temperature zones. Now the red zone is too hot for water. The cold zone or the blue zone is too cold for water, and while the green zone is just right for water to exist as a liquid. Venus is in the red zone, Earth in the green zone, and Mars is in the blue zone. Um, so as you can see, um, Venus has a temperature of about 480 degrees Celsius, while Mars has a temperature of about an average. Now the minimum temperature can go down to about -60, with the maximum during the summer months up to 20 degrees Celsius, while Earth, its average temperature is about 15 degrees Celsius, though the minimum temperature ever recorded, or the coldest temperature ever recorded, was at, if I remember correctly, at Vostok Station in Alaska, Antarctica, where it reached a temperature of minus 89 degrees Celsius, while the hottest one was in, if I remember correctly, in Egypt. Okay, I will correct myself in the next video. Myself I just need to look that up for the next video. But the hottest temperature recorded was 58 degrees Celsius. Now I need to look that up as well. Note to self, look the temperature up as well, with more names of planets and their masses for the next video. Yeah, note to self. But yeah, that's and this is for every star, though the distances of these zones is maybe further or closer to the star, um, with hot blue blue stars like Rigel, for example. These zones are very far from them, from the stars. Um, the hot blue zone, red zone, would be um, round about where Jupiter would be in our system, or further. Um, I I can't get any information on that. But around hot blue stars, for example, these red, green, blue zones are more or less where the gas giants would be in our system, more or less. Um, and around red dwarf stars like TRAPPIST 1, they are much closer to their to the stars than Mercury is. Um, this is because red dwarf stars are basically tiny in size and mass. Now you could basically make about a dozen or so red dwarfs from the sun. Yeah, the smallest red dwarf stars have a mass of about 0.08% the mass of the sun. So they have a mass of about 0.08% that of the sun. So, and some of the smallest of these stars are barely bigger than Jupiter. Um, so now the diameter is just slightly bigger than Jupiter. However, their mass is several times higher than Jupiter. Now, the smallest possible mass for a red dwarf is about 80 Jupiters, as in 10 times 8, 10 times 8, the mass of Jupiter. Now, one would think that the more mass you add to an object, the bigger it gets. However, at at a certain point, um, that does go on. The more mass you add, the bigger an object gets. However, if you keep adding mass, gravity will start pulling the object into a smaller shape or sphere. Um, Basically, gravity shrinks the object down with more mass. The more gravity it has, the more it shrinks itself until um, with the smallest red dwarfs, you start having proper hydrogen fusion, though at an extremely slow pace. Now the sun, for example, as a can last up to 10 billion years, and the sun was born about 4.6 billion years ago. So there's about another 5 to 6 billion years for the sun before it dies. However, red dwarfs, um, yeah, they can last a whole lot longer than our sun. As in, for every year that the sun lives, a red dwarf can last 100 years. So basically, our sun can last 10 billion years. A red dwarf, like TRAPPIST 1, um, unknown. But, okay, not that unknown. It's estimated that a red dwarf can last something like 10 or more trillion years. Yeah, that's long. Something like 10 trillion years. Yeah. Um. So they can last, or any planets that they have can last just as long. However, red dwarfs like TRAPPIST 1, they produce large scale bursts of radiation and flares. Um, Now, by this one red dwarf, I need to look that up again, the name, but the names that they sometimes use, okay, even though I'm really good with astronomy, some of the names that they use are just, yeah, they're too much for me. I can't remember every one of these names that they use, but with this one red dwarf that they monitored over a period of 84 days, they registered 42 major flares. So basically, one flare every 2 days. Yeah, that's actually quite heavy. The sun, over the same period, produces maybe two, two or three flares over the same period. So this red dwarf was a heavy producer of these flares. And these flares release a huge amount of radiation, X-rays and other kinds of radiation. And these flares that they registered, they were really massive. Some of the biggest flares were as big as the 1859 Carrington event. Now, in 1859, the sun produced a pretty big solar eruption which affected the Earth a few hours later. Now, the communication system that they had at that time, the telegraph system, um, yeah, that was affected quite severely. In some places, they disconnected the telegraphs, but were still able to send messages via the electrical energy in the atmosphere. And these batteries that they used to charge the telegraphs in some areas, they were being charged up. And the auroras, um, normally the aurora borealis or northern lights are normally seen in Canada, Alaska, um, Russia, Sweden, Norway, Greenland, Iceland, normally. But in 1859, these northern lights went as far south as, they went as far south as the Caribbean, Florida, Hawaii, Philippines, for example. Basically, the entire northern hemisphere could see these northern lights. And this red dwarf, over a period of 84 days, produced several of these sized events, eruptions, or flares. If such a flare were to occur today, well, there go all the first world countries: Canada, US, Russia, Germany, the UK, Iceland, basically almost the entire northern hemisphere would be out in the dark for a few decades or so, because this event, this Carrington-sized event, would yeah fry most of our electrical systems. Power lines would be overloaded. Power stations would be knocked out. Transformers, they're gone. So most electrical grids would be gone, and it would take a few decades or so to recover from that. And I don't need to tell you what would happen if the almost the entire northern hemisphere would be wiped out by such an event. If you think the global recession from 2008, or the Great Depression in the 1930s were bad, yeah, this one would be worse. And it would take decades for the entire world, if not longer, to recover from that knockout blow. But onto the main theme. These kinds of flares for red dwarfs and their planets, well, mostly for the planets, would be really, really bad because these kinds of flares can strip the atmospheres of any planet or planets around a red dwarf star in just a few million years. Just one flare, and it would take thousands of years for the atmosphere of these planets or planet to recover. Um, I read in an article a while back that it would take something like 30,000 years for the atmosphere of a planet to, or the Earth, for the Earth's atmosphere to recover if it were hit from a normal sized flare from the Sun. Now, with red dwarf planets, they are extremely close to their planets. Sorry about that. Stars. I meant to say star. Um, Even the furthest planet from a red dwarf star would still be inside um, Mercury's orbit. That's how close they are to their red dwarf host. They are normally less than 60 million kilometers from the red dwarf star that they're orbiting. So, first of all, they are tidally locked, or at least it's believed that most planets that orbit that close to a red dwarf are tidally locked, meaning they always show the same side to the red dwarf, while the other side always points away from the red dwarf. Basically, it's the same thing with the moon. Well, our moon. We always see the same side of the moon because it is tidally locked to the earth. We always see the near side of the moon, but the far side only if we send a spacecraft to that side, or during certain points of the moon's orbit. There we see um I can't explain the thing right now. Need to look up that again. But during the moon's orbit around the sun, the Earth, sorry about that. During the moon's orbit around the Earth, um, we sometimes see parts of the far side, up to 9 or 10% of the far side, because of the orbit shape and the way the moon is tilted compared to Earth. The moon's orbital tilt compared to the Earth, meaning that we sometimes see part of the moon's far side. Now the same would be with planets around red dwarfs. One side always faces the star, while the other side always points away. Um, which means one side has permanent day and the other side permanent night. And this poses a problem because it may mean that these planets might not have a magnetic field, because from what we've observed here on Earth, part of the magnetic field that we have, from what we've observed so far, is because of the Earth's spin, also because of convection inside Earth's core. Now I will explain more about this in a later video, but the Earth's magnetic field comes partially from convection currents and from convection currents inside Earth's core and from Earth's spin. Now, because red dwarf planets are tidally locked, or at least we strongly believe they are, well, belief might not be the right word, but the evidence, or at least what we may see, I'm not sure how to say this properly, but now because they orbit so closely to the red dwarf star, the star's gravity may have locked these planets tidally to it. So now what I'm trying to say is many astronomers think that planets that orbit red dwarfs are tidally locked, and because of that they might not have a magnetic field, or at least not as strong as Earth has, or Earth's magnetic field, because like I said, part of the magnetic field that we have here may be a result of the Earth's spin, and because red dwarf planets are tidally locked, their magnetic field might not be as strong as Earth's magnetic field. Um, Now they may have some convection currents inside them, which may give some magnetic field, but yeah, it might not be as strong as Earth's magnetic field. And whenever they're hit by a stellar flare from one of these red dwarfs, yeah, that affects their atmosphere, and a part of the atmosphere is just gone. Not that much, but over millions of years, that adds up. Every stellar flare, there goes another part of the atmosphere. There's another one, another, another, and it goes on and on and on for millions or billions of years. So, red dwarf planets may actually lose their atmospheres because or partially because they might not have a magnetic field, or at least not that strong as Earth's, or um, at least that's where the evidence may point at. Um, but right now, further research must be done on this, because we don't have all the answers on this yet. But over the years, as more research is done on this, we will find out whether red dwarf planets, firstly, are tidally locked, and if they have a magnetic field or not. But research is still being done on this, so we will see over the next few years or so. Um, yeah, that's about it for now. Need to wrap this video up for today. I've been rambling on too long for today. Don't want to make this video too long, otherwise it's gonna take an age and a half to upload. Seriously, it's this one's been long. Probably the longest one I've made so far. But I will look up those names of those planets and that other thing as well, if I can remember. Um, what was it again? Oh man, I lost the thought. Um, guys, please, if I don't remember it, please remind me, or I'll just look it up in the video again. Yeah, I'll just do that. But this is it for now. Peace out, guys. And yeah, this is it for the Starstruck Rambler for today. See you next time. How is the finger?